Welcome, everybody. Please keep eating. I want to go ahead and start the program, and because I want to be respectful of your time on the backside of the event. So I'm Steve Dunn. I'm the local public policy chair for our Hampton Roads section of the AIAA, and work for Jacobs. Been out here at Langley for about almost 20 years now in various roles, and really appreciate being part of the Hampton Roads AIAA. If you're not part of that, I encourage you to look into it. It's a great group of people, I think, doing meaningful work in a lot of different areas. This is booked under public policy. It's called the Wright Brothers Lecture. I won't. It's something that's been going on for a long, long time, and I think we have a great speaker today. And so let me make introductions, and with that, then I'll turn it over to Dave. Beware today. I think it's really neat. Beware of what you don't know. You don't know. Real world lessons. And this is in space, but I think it applies. I work in ground test a lot. I think it has safety and work quality implications. We've got a lot of new people in our workforce, a lot of new smart people, maybe some of them with a lot of experience, but maybe not here. So there's a lot of things that I think there's some lessons here that we can all maybe learn from. I know I can. So with that, David Throckmorton is the recently retired Vice President for Research at the National Institute of Aerospace. Prior to joining the NIA, he had served as the program manager for Northrop Grumman on the Langley Research Center's Technology, Engineering, and Aerospace Mission Support Teams contract. And before joining the contracting world, he completed a 37-year career with NASA at multiple field centers. Early in his NASA career, 30 years of which were at Langley, he performed hypersonic wind tunnel tests of candidate configurations for the Space Shuttle orbiter and was one of NASA's principal interpreters of flight data from the orbital flight test missions of the Shuttle Columbia. Over the course of his NASA career, he served as assistant head of the Aerothermodynamics branch and manager of the Space Transportation Programs Office at NASA Langley, director of base technology for the National Aerospace Plane Program in the NASA DoD Joint Program Office, deputy director of engineering at the NASA Marshall Space Flight Center, and deputy director of the NASA John C. Stennis Space Center. Mr. Throckmorton earned his BS and MS degrees in aerospace engineering from Virginia Polytechnic Institute and George Washington University, respectively. He's the author or co-author of more than 50 technical publications. He's a fellow of the AIAA and recipient of numerous awards, including the NASA Outstanding Leadership Medal. So with that, Dave.
Thank you. Thank you. Does this thing work? Are you hearing through the cool? Good deal. Well, again, thank you so much, Steve, for the invitation, to make this presentation. Much appreciated. Before I start, let me just throw in for those of you who are AIAA members or those of you who may not be, particularly you young folks, I really, really, really want to encourage you to get engaged with AIAA. Go to write papers, go to conferences, make presentations, potentially get yourself involved in technical committees if you can. I look back over the length of my career, and I will tell you, I have personal relationships with more people across the breadth of our industry at every level, from working engineer to CEO, that have really, I think, in some way, shape, or form, have enhanced my personal career. And it's not because I was a good engineer at NASA Langley with my head down and my crayons out doing my job. It was because AIAA gave me the opportunity to create networks across the industry. So, that's my pitch for AIAA as an organization, and I would really, really encourage all of you to get involved to the degree you can and wish to do so. So, our presentation today, as you can see on the title slide, beware what you don't know, you don't know. I've got some examples here of examples of systems engineering that maybe didn't quite evolve the way they should have. Several of them I had personal engagement in. Several of them I just have knowledge in. There are a couple other folks of my generation in the room who may know some of this better than me. So, gentlemen, if I misspeak, please raise your hand and say, "Wait a minute, David, you got that one out of context." All right. So let's talk about how you certify space systems for flight. Well, there are basically three ways you go about it. You certify them for flight because of the quality of your design and your analysis of the systems themselves. The other way you certify things is put them through test and prove that they do what you've designed them to do. And then lastly, and this is an issue that I'm going to talk about here, oftentimes we use similarity. Well, we did it this time last time, and it was successful. So we're going to use the same concepts and maybe even the same hardware another time and certify for flight based on that heritage or that similarity. So I've got 4 stories I'm going to tell you today. One about the Space Shuttle Orbiter, one about the Pegasus launch vehicle, one about the Genesis spacecraft, which was a spacecraft that went out and sampled particulates from the solar wind, and the last one was Mars Pathfinder. These are not necessarily all horror stories, but they certainly had the potential to be that. So let me first talk about a method of certification by design and analysis. And my example here is going to be the Space Shuttle's thermal protection system. The Space Shuttle Columbia was delivered to Kennedy Space Center in March of 1979. And you, sir, may know if I'm wrong, but my recollection back then was the vehicle was not really ready to be delivered from Rockwell International to NASA. But there was a contract milestone that said, hey, you got to turn the vehicle over to NASA. So it was delivered to Kennedy Space Center in March 1979. And here's a picture, and you'll note that the thermal protection system all over the vehicle is potted with places where there is no thermal protection. And so at Kennedy Space Center, a role that the technicians there had that was never initially anticipated was to apply thermal protection system tiles all over the vehicle and test them to ensure that they were structurally sound. So here's a picture of the lower surface of the vehicle and the so-called high temperature reusable surface installation tiles. And if you've never seen one, you know, I've got one that you guys can pass around and put your fingers on. The tiles themselves were made of pure silica fiber, but the silica fiber in these structures is 99% void, and that's how the tiles get the extreme thermal insulation what's the word I'm looking for? Characteristics that they have. Okay. But to put them on the vehicle, the way it worked was you got the tile. It has on top this RCG, which is reaction cured glass coating, and you can see that on that example. That's the black coating. The black coating did 2 things. It waterproofed the tile to keep moisture out of that 99% void of the silica fiber, and it also provided a surface that was very good at emitting heat back into space. You know, it was a good emitter, okay? Well, underneath the tile is an RTV adhesive that attaches to a strain isolator pad. And in the sample I'm sending around, you can see remnants of the strain isolator pad underneath there. And then there was some more adhesive, and that attached it to the aluminum skin. And the reason it was done that way was, number one, if you think about it, when you're sitting on the ground in Florida at maybe 100 degrees, you have one configuration. When you go into orbit and you're facing away from the sun, you know, it's extremely cold. So there were 2 things that the filler material did. It provided some thermal expansion and contraction based on the different temperature environments, but it also provided a buffer for any kind of structural deformation that might happen. So when the orbiter was sent to Kennedy Space Center, they started doing pull tests on the tiles. Now, the reason you do a pull test is, like I said, this right here is 99% void. So think about it. You're sitting on the ground at ambient pressure, you know, in Florida. As you launch, the external pressure in the air is getting lower, lower, lower until finally you get into space. And of course, you got none. So there's concern about, you know, due to the pressure differential, you know, is the tile going to be subject to popping itself off? Now, it wasn't so much just the ambient change in pressure, but rather when you're on the launch vehicle and you have a shock wave come and cross a tile, you can have a very instantaneous change in the external pressure. So you can go from one level of pressure to another one all of a sudden And so there's concern that you have sufficient strength in this whole system to take care of that pressure differential. So if you look at the ultimate tensile strength of the various elements that made up the system, well, the tile itself was good for 24 pounds per square foot tensile strength. Okay, the strain isolator pad was good for 48 pounds per square foot. You know, the RTP adhesive was enormously strong, but when they did a systems level test, these things failed at approximately 11.7, 12 psi. Oh my goodness, what was all that about? So there was a significant effort to understand why is the system weaker than any one of its individual parts. And the answer turned out to be, I think right here, the failure point was this interface between the strain isolator pad and the reusable surface insulation material itself. Langley Research Center, particularly under the leadership of Jim Starnes, was very, very engaged in trying to understand what happened here. And what they ultimately found out was, well, when you pull the tile against this strain isolator pad, because the tile is all these various fibers, what you end up doing is you create localized, very, very high stress areas in excess of the basic capability of the tile itself. And so there's where the system failure was. And the solution turned out to be to densify that back face. So what they did was they made a slurry of this RSI silica material and kind of infused it in the bottom of each tile to a depth of, I don't know, 1/16 of an inch, an eighth of an inch, something like that, which when you pulled on it, the individual fibers in the tile then were not overstressed. So again, kind of a horror story that could have been, turned out was not. And Langley Research Center had a very significant role in understanding what the issue was and proposing the solution for that one. So let's talk about certification by testing. Langley was again very intimately involved in the definition of the aerodynamic characteristics of the shuttle orbiter. Couple fellows in our old Space Systems division by the name of Bernie Spencer and George Ware traveled the country doing wind tunnel testing in support of the space shuttle program to understand the aerodynamic characteristics of the vehicle. And pre-flight, this is what the pitching moment looked like, we thought. Now, notice the Mach number scale here, because I'm going to flip it over in a minute, and it's going to be confusing if you didn't pay attention. So you know, whoop, too quick. High Mach numbers here. So we're coming out of orbit, and we're coming this way, and you can see what the anticipated pitching moment was, and the presumed pre-flight uncertainty band. Oops, on STS-1, this is what the pitching moment turned out to actually be during entry. Not only was it different from what we thought it was going to be pre-flight, it was outside the uncertainty band of what we thought it would be pre-flight. And the issue here is primarily the fact that we were doing wind tunnel testing on models that were 1 foot long, maybe 10 inches long in hypersonic ground test facilities. And you're extrapolating that information to a vehicle that's 107 feet long, you know, in flight. You're also extrapolating it into a thermochemical environment where you're not dealing with perfect gas anymore. You're dealing with chemical reactions that happen in the flow as the flow goes through the shock wave. So what did that mean in terms of the ability to keep the vehicle stable during entry? Again, here's looking at the body flap deflection, and here's where I flipped the Mach number on you. So high Mach numbers on the left and low Mach numbers at the right. The pre-flight prediction was, well, we thought we'd have to keep the body flap at about 7.5, 8 degrees deflection. The maximum deflection limit was up around 22 degrees. So we had plenty of play in the body flap, one thought. But here's what the flight data look like. You know, this is a result of that pitching moment discrepancy I showed you. The body flap at high Mach number was actually out up here in the 16, 17 degree deflection range to keep the vehicle stable. Turned out you had plenty of mechanical capability to do that. But the other issue is, well, what happens when you drop this body flap down hypersonic speeds? What happens to heat transfer on the body flap? And the answer is, oops, you almost created a situation where the temperature level on the body flap was in excess of the capability of these high temperature reusable insulation tiles I showed you. You know, I guess what I would say is here was a situation where we dodged a bullet, learned a lot, but you know, what we thought the case was going to be pre-flight turned out not even to be very close post-flight. So why was that the case? And I kind of touched on it. Here's an example of some wind tunnel Schlieren measurements. Here is the shock wave. If you got the vehicle at Mach 6 in air at a specific heat ratio of 1.4, which of course is what we have in our wind tunnels here on the ground. But if you look at what actually happens in flight at Mach 24, the ratio specific heats in this reacting gas is substantially different. And as a result, you would anticipate a shock wave that is much, much closer to the vehicle surface. And then we have post-flight measurements here from Langley's CF4 tunnel, which comes close to matching the ratio specific heats. And so there's the primary issue. Back when we were doing all of the testing of shuttle aerodynamics to understand what they were, we didn't have the capability to do some of these thermochemical calculations. You know, CFD was in its absolute infancy back then, and we didn't have a CF4 tunnel that we could go and try to on the ground simulate, you know, what that looked like in flight. So that's one example. Now here's another one: certification by testing or not, I call it. Orbital Sciences Company back in the late 80s decided that they were going to create a launch vehicle to take small payloads into orbit. It was a launch vehicle that didn't take off from the ground. It would be dropped from a carrier aircraft. And the vehicle was called Pegasus. They commercially developed it and then you know, brought a capability to the table that had not existed before. The air launch of this thing was at 40,000 feet. About Mach 0.8, and initially they used NASA's B-52 as the carrier aircraft to launch Pegasus. Later they got a DC-10, DC-10 that you see there. So they owned the DC-10 and they owned the Pegasus launch vehicle. It was all completely their thing. However, their first half a dozen, I think it was 8 maybe, missions of Pegasus where they dropped it off the B-52 were successful. They were successful, and they said, "Oh, this is good. We're getting this L-1011. We've demonstrated the capability that we can do this. Let's enhance our capability." So they proposed to put 2 plugs in the configuration to enable a greater fuel load that would let them take heavier payloads, but they had to change the design of the tails. You'll see here when in the original standard configuration, the tails were horizontal. When they went to the so-called XL configuration, those things were drooped down, and they had to droop it down to keep those away from the gear doors on the back end of the L-1011. Now, my comment about certification by testing or not is that they originally certified this thing aerodynamically without any wind tunnel testing. They used a capability for missile aerodynamics. And you think about missile aerodynamics, for missiles, you know, they're circular. What's the word I'm looking for? It doesn't matter which direction the missile goes, so to speak. You know, the aerodynamic forces are going to be the same because you got a cylindrical missile and you got force fins. Well, they used missile aerodynamics code, you know, to design this thing here, and they were successful flying it. But there was an indicator in their flight test data, or their not their flight test data, and there was an emphasis in their flight data that maybe something about using that missile code wasn't quite right for this thing, which was actually a lifting body. So I'm going to show you that. This is a history of side slip angle from a number of their initial flights with the standard configuration and the side slip angle on the very first flight of the so-called XL configuration that had the droop tails. And the thing that they didn't pay attention to in hindsight is every time they flew this thing, they had this thing that ended up being called the whoop-de-doo, that they would release it shortly after drop, the side slip angle would start getting large, but it didn't get so large that they lost the vehicle. It would come back and they flew successfully. On the first flight of the so-called XL configuration with the droop tails, well, here's what happened. And this was the landing of the Pegasus XL on its first flight. The other thing I want to tell you, and here again is a NASA Langley story. A fellow by the name of John Paulson that some of you may know was kind of a key participant in understanding what had happened here. Let me go back. You'll see on the right, well, in both of these pictures, there is wind tunnel testing going on. And that's wind tunnel testing that was actually performed after the failure of the Pegasus XL to understand what the issues were. With the help of NASA Langley and John Paulson and the people in his experimental aerodynamics branch, they understood the problem, fixed the problem, and Orbital Sciences was flying Pegasus. They may still be flying them for all I know, but for many, many years, Orbital Sciences flew their Pegasus launch vehicle for putting small satellites into orbit cheaply. Okay, so. All right, now I've got two other examples of talking about certification by similarity or heritage. This first one, the Stardust spacecraft was a mission to send a spacecraft to fly through the tail of the comet Bield 2, collect samples of the cometary dust, and bring it back to Earth. The launch of this vehicle, as you can see, was in 1999. It came back and landed in 2006, and there is the entry capsule upon landing in the Utah desert. And here's some of the cometary dust that was collected during that mission. There was a subsequent mission to do something very similar called Genesis. And the objective of Genesis was to send a spacecraft out into the solar system to sample the solar wind and bring back samples of the particulates that are part of the solar wind. It was launched in 2001, landed in 2004. However, on its entry, this is what happened in the Utah desert. The vehicle came through the atmosphere, did not slow down, and crashed into the Utah desert, you know, half a meter, 2/3 of a meter into the ground. Now, it turned out that they were able, even though you can see the come on, baby, here we go. Even so, you can see the damage to the spacecraft. You know, they were able to gather some scientific results from this mission. But you know, the question is, what in the world happened here? We did it the first time on Stardust, and everything was hunky dory. Here we try to do the same thing, and we crash in the desert. Well, the answer turned out to be very straightforward. Once a mishap investigation board went and looked at it, Uh, both spacecraft had these little G switches in the electronics, and the G switch was to sense the aerodynamic deceleration of the spacecraft as it came through the atmosphere. When the deceleration became significant, you pop the parachute and you drop down to the Utah desert, very easily. Problem was, same G sensors, and if I remember the mishap investigation report, the same electronic board, essentially no changes. The problem was the G sensors were installed backwards. And there was no testing done to demonstrate that they would perform as they were supposed to. So they were installed backwards. The spacecraft comes into the atmosphere. The G sensors say, "Hey, I'm not sensing any deceleration, so I'm not going to pop the parachute." And so that's what happened there. All right, and then my last case study about heritage and similarity is one that engaged NASA Langley very, very directly. Project Viking, for those of you who are insufficiently old enough to know these things or don't know about your history, Project Viking was a NASA Langley project to send 2 landers to the surface of Mars back in the mid-70s. The first set of scientific experiments to literally land on the surface of Mars. The project office for Viking was right here at Langley. This is a picture on the left. That's Carl Sagan, the planetary scientist, standing by a mock-up. I think that mock-up is in the Virginia Air and Space Museum down in Hampton now. Either this one or something similar used to be. So you can get an idea of scale there. So 2 Viking spacecraft were launched, both in 1975. They both landed in 1976. Very successful program. So here's this next Mars lander project called Mars Pathfinder 20 years later. And the Langley story here is, because of my engagement in AIAA nationally that I talked to you about, I get a phone call one day from a guy from JPL. Never worked with him before, but knew him by way of our AIAA national engagements. And he says, "Hey, Dave," he said, "I've just been identified as the new chief engineer for a project called Pathfinder." He said, we're going to send a spacecraft to Mars to put a little rover on the surface, and we're going to do it just like Viking." Said, "But we're going to spin stabilize this thing on the entry, and we're a little concerned how close to the axis of symmetry do we have to keep the CG so this thing is stable. Do you have anybody that could do some analysis for us and help us out with that?" And I said, "Sure, we can do that." So, if you weren't familiar with Pathfinder, there's the spacecraft, there's the launch, and instead of dropping it on a parachute or with retro propulsion like we've done with the Mars landers recently, they slowed the thing aerodynamically in the atmosphere, popped the covers of the spacecraft off, inflated these balloons, and the thing bounced on the surface of Mars in these balloons until it came to a stop. So he says, we're going to do it just like Viking, but we need to know something about how we do our center of gravity. And I said, "Sure, we can help you with that." So probably a week later, we had arranged for a telephone call with this guy. And I get in the room. I'm in the room. A young whippersnapper at the time by the name of Bobby Braun. Some of you may know that name. Bobby was in our vehicle analysis branch, and he was doing trajectory simulation stuff and vehicle dynamics. Bobby was in the room. A researcher by the name of Peter Naffo was in the room, who was the individual that created the LoRa code, one of the very first non-equilibrium fluid dynamic codes for hypersonic flows. And a guy named Vince, who was also in the aerothermodynamics branch. Vince had history back to Project Fire, which was a flight test back in the day to demonstrate that the thermal protection system for the Apollo modules was okay. So we're in the room, and we got we got this guy at JPL who is seeking our help. And don't recall who was with him, but those were the Langley cadre of fun people. So this guy begins to talk about and educate all of us about what they're going to do. So first of all, the entry vehicles are very similar. They were both 70-degree spherically blunted sphere cones. The Viking one, you'll see, was a little bit bigger than the Pathfinder one, but geometrically, they were very, very similar. So before I go through the rest of this story, for those of you who are not aerothermodynamicists, let me just show you an equation real quick. This is the Fay and Riddell expression that we used to use back in the day to estimate what the heat transfer to the stagnation point of a vehicle entering an atmosphere hypersonically would be. And I just want to point out a couple of things to you. So the heat transfer rate as the density goes up, as you're coming into the atmosphere, whether it's Earth's atmosphere or Mars, the heat transfer goes up with the square root of the density of that atmosphere. Okay. As the nose radius gets smaller, the heat transfer goes up as the square root of the nose radius. Two important points. Probably the most important point, though, is heat transfer goes as the cube of the velocity. So now we get in this conversation of what it is JPL wants to do and how similar it is to Viking, and we'll see whether it was or not. So first of all, cone angles are identical. No issue whatsoever. The diameter, Pathfinder's a little smaller than the diameter of Viking, and so our heat transfer guys say, hey, because the diameter's smaller, your heat transfer might be a little higher than Viking was. Check. We probably ought to concern ourselves with that, right? Okay. Well, nose radius is directly related to the diameter, so that's kind of the same story. Nose radius goes down, heat transfer goes up a little bit. The entry mass of the vehicles was much different. Viking was like 930 kilograms. Pathfinder was 585. And so when you look at the mass, you look at the size of the things, there's a parameter called ballistic coefficient. And it turns out that the ballistic coefficient for both of them was about the same. And so what that means is, even though they're different sizes and different weights, the way those two things trade off to one another, they would kind of fly the same entry trajectory, into the Martian atmosphere, right? Okay, whoop, first, real gotcha. He said, we're going to spin stabilize this. And, one of our guys with experience in Viking says, wait a minute. Viking was not spin stabilized. Viking was inertially stabilized. And oh, by the way, it didn't come in at 0 angle of attack. It came in at 11 degrees angle of attack. So the distribution of heat transfer that you're going to see on this vehicle is potentially substantially different than what we experienced on Viking. And so that was kind of the next check. Oh, I guess we need to worry about that. We'll pay attention to that, right? The coup de grace was when he said, oh, by the way, he said, we're going to make a direct entry into the Martian atmosphere from a trans-Earth trajectory at 7.6 kilometers a second. And Vince Zobie, my cohort in the aerothermodynamics branch, about went through the ceiling. He says, you're going to do what? They didn't, they may have recognized, but they didn't realize Viking first went into Martian orbit. And then they released the spacecraft out of Martian orbit. So, Viking went into the atmosphere at that speed. Pathfinder was going to go in at that speed. And oh my, what does that mean? Peak heating rate is going to be increased by a factor of 4. The rest of this story is, as a result of that conversation and us making them aware of that, I want to tell you that, Daryl, you were probably there at the time. It didn't take but a few weeks, maybe a month or two, before JPL Langley and said, Langley, would you please take responsibility for doing all of the entry, descent, and landing analysis for us? And that's why here we are 30 years later almost, that Langley is still doing entry, descent, and landing work in support of JPL missions. And of course, I I'll get to that in a minute. So having observed this stuff, our computational fluid dynamicists went to work, our aerodynamicists went to work. What you find is, even at zero angle of attack, if you got a little bit of wiggle in the spacecraft away from zero, what happens is you get, and make sure you know what I'm looking at. This is the forebody at 2 degrees angle of attack at Mach 22, Mach 16, and Mach 9. And what you see is that the shock wave on one side is very close to the vehicle. On the other side, you have this subsonic bubble. So what it's doing is it's imposing a pitching moment on the vehicle. So it's not going to sit there at zero angle of attack. It's going to want to move. Okay. And how it moves at Mach 22 and how it moves at Mach 16 and Mach 9 are substantially different. What does that mean to the static stability of the vehicle during entry? Here's the analysis that shows you there were actually 2 regions where the vehicle was statically unstable. So even they're rotating it, to keep it stable, but aerodynamically it is not. And here are the constructions of what the angle of attack looked like during the entry as a result of that stuff. And these 3 kind of technically detailed slides I've showed you are all products of folks here at Langley that were trying to help JPL understand what they were facing and help them ensure that the vehicle was successful. And of course, in the end, it was. The Pathfinder spacecraft took the little Sojourner to Mars and landed in July 1997. And it was kind of the initial foray that our agency has had in putting scientific rovers on the surface of Mars. I know many of you in the room here are familiar with the latest one, that you were probably intimately involved in the analysis and the design to make that a success, which it was. But again, my message that I think is important for folks at Langley to know, there was a point 30 years ago where JPL didn't know what in the world they were doing, quite frankly. And they did not know that they did not know, is the point. And Langley has been in the mix for Mars missions ever since. That's my story, and I'm sticking to it.